Across the universe, motion is usually relative. Speeds change with perspective, directions matter, and movement depends on where it is measured from. Yet light does something unexpected. When it travels through empty space, its pace remains fixed, regardless of how it was produced or how fast anything nearby is moving. This behavior has been observed under many conditions. Light emitted by distant galaxies arrives with the same underlying speed as light generated in controlled laboratory experiments. The circumstances vary widely, but the outcome does not. Careful measurements show that this speed does not adjust to match the motion of its source. It does not respond to the motion of the observer. Distance, direction, and time leave it unchanged. At human scales, this feels unfamiliar. Everyday motion is additive. A moving platform changes the speed of what is launched from it. Experience builds intuition around these patterns, and that intuition works well within ordinary limits. When applied to light, however, those expectations stop being reliable. Experiments continue to return results that resist adjustment, even as methods become more refined and instruments more precise. This understanding did not emerge from a single discovery. It formed gradually as observations accumulated and descriptions of motion were forced to accommodate a constant that refused to vary. As precision improved, disagreement diminished. Each refinement tightened the picture rather than complicating it, reinforcing the same conclusion across different approaches and scales. To understand why this happens requires looking beyond familiar ideas of speed and motion and toward the deeper structure that connects space, time, and measurement themselves. Welcome to The Sleepy Scientist. If you enjoy conversations that unfold at a far slower pace than light itself, you are very welcome to stay. And if you feel like it, you can share where in the world you are listening from tonight. For most of human history, light did not feel like something that needed explanation. It appeared instantly. A flame was struck, and the room was illuminated. The sun rose, and the world was suddenly visible. There was no obvious delay, no sense of travel, no hint that light moved at all. It simply arrived. That impression shaped early thinking for thousands of years. Philosophers in ancient Greece debated whether light streamed outward from the eye or entered it from the world, but many shared the same underlying assumption. If light moved, it did so infinitely fast. Faster than arrows, faster than sound, faster than anything that could reasonably be timed. For everyday experience, that assumption worked perfectly well. Yet modern experiments reveal something quietly unsettling. Light does move, and when it moves through empty space, it does so at one specific speed. Not approximately, not on average, but exactly the same every time it is measured, regardless of how fast the source is moving or how fast the observer happens to be. That detail alone would be strange enough, but it becomes far stranger when compared to how motion usually works. In daily life, speeds are relative. A cyclist moving down the road throws a ball forward, and the ball's speed adds neatly to the cyclist's motion. A train passes a platform, and its velocity depends entirely on where the measurement is made from. These ideas are so deeply embedded in experience that they rarely feel like assumptions at all. They feel like facts about how the world behaves. Light refuses to follow that pattern. Measurements show that light emitted from a stationary lamp and light emitted from a rapidly moving source both travel through empty space at the same speed. If an observer moves toward a beam of light, the light does not appear to approach faster. If the observer moves away, it does not slow down. No matter how the experiment is arranged, the result comes back unchanged. This behavior is not subtle. It is not buried in noise or statistical ambiguity. It is one of the most thoroughly tested results in all of physics. The speed itself is immense. In a vacuum, light travels at roughly 300 million meters every second. That is fast enough to circle the Earth more than 7 times in the blink of an eye. At that pace, light could travel from the Earth to the Moon in just over 1 second, and from the Sun to the Earth in a little more than 8 minutes. Yet the number is not the most important part of the story. What matters is that the number does not budge. This constancy clashes sharply with the expectations built from everyday motion. According to common sense, if a source is already moving, whatever it emits should inherit some of that motion. Sound behaves this way. Water waves behave this way. Thrown objects behave this way. Light does not. For centuries, this difference went unnoticed simply because the speed involved was too great to test. Human reactions are slow. Early instruments were crude. Any delay light experienced over ordinary distances was far too small to detect. A torch across a room illuminates the wall so quickly that no human sense can perceive the travel time in between. That limitation encouraged the belief that light speed was either infinite or irrelevant. Even when early scientists began questioning that assumption, the challenge remained formidable. How does one measure something that crosses familiar distances faster than any clock can tick? Despite these obstacles, the idea that light might have a finite speed slowly gained traction. Astronomical observations hinted that light from distant objects might take time to reach the Earth. Careful comparisons of eclipses, planetary motions, and celestial events suggested tiny delays that could not be ignored forever. What emerged was not a neat answer, but a widening gap between expectation and observation. If light had a speed, it was extraordinarily fast. If that speed was finite, it was still vast beyond intuition. And if that speed was fixed, rather than relative, then something deep about motion itself would need rethinking. This is where the question begins to matter. The speed of light is not just a property of light. It acts as a reference point for the structure of physical reality. Time measurements, distance measurements, and even the order in which events occur turn out to depend on it. Long before those consequences were understood, however, the stubborn consistency of light's speed was already pointing toward them. One of the first to grasp the seriousness of this implication was Albert Einstein, who recognized that the constancy of light could not be explained by adjusting the behavior of light itself. Instead, the adjustment would have to come from something far more familiar and far more unsettling: time and space. But that realization lay ahead. At this stage, what matters is the mystery itself. Light behaves in a way that everyday motion does not prepare the mind to expect. It carries speed without inheriting motion. It moves through empty space as though guided by a rule that everything else must adapt to. This chapter does not attempt to resolve that rule or explain its origin. Its purpose is simpler and more foundational, to establish that the question exists at all, to show that the speed of light is not a technical detail buried in textbooks, but a central feature of how reality behaves when examined carefully. The puzzle is not that light is fast. The puzzle is that it is precise. That precision is not imposed by measurement conventions or human definitions. It reveals itself independently, across different experiments, different observers, and different circumstances. It appears in laboratories and in astronomy alike. It holds whether the source is at rest or racing through space. Once that fact is accepted, the natural response is not to ask what light is doing, but how anyone could possibly have discovered this in the first place. And that question leads naturally to the long, careful process by which humans first learned to time something that seemed untimable at all. Trying to measure the speed of light turned out to be one of the most quietly stubborn problems in the history of science. Not because the idea was complex, but because the thing being measured seemed almost unwilling to cooperate. Light moved too quickly, over distances too short, for early tools to register anything useful at all. For centuries, the difficulty was not philosophical but practical. Clocks were slow. Human reaction times were slower. Even the best instruments of the early modern world could not resolve intervals small enough to catch light in transit across familiar spaces. A flash across a room appeared instantaneous. A signal across a city arrived with no perceptible delay. From the perspective of everyday measurement, light behaved as though it had no speed worth discussing. Early thinkers were not ignorant of the problem. Galileo Galilei himself attempted a terrestrial measurement in the early 17th century. He and an assistant stood on distant hills, each holding a lantern with a shutter. One would open the shutter, the other would respond upon seeing the light, and Galileo would attempt to measure the delay. It was an elegant idea. It was also hopeless. The distance was too short, the reaction times too long, and the result inconclusive. Galileo correctly concluded not that light was infinite in speed, but that it was simply far faster than his method could detect. That distinction mattered. It kept the question alive. If light could not be timed on Earth, perhaps it could be timed in the sky. Astronomy offered distances far beyond anything available on the ground, and with them, the possibility that even light's remarkable speed might finally leave a detectable trace. But even here, the challenge was subtle. One needed a clock large enough, regular enough, and predictable enough to reveal tiny delays accumulated over vast distances. That clock arrived in the form of the solar system itself. In the late 17th century, astronomers were carefully tracking the motions of Jupiter and its moons, not out of curiosity alone, but for navigation. The eclipses of Jupiter's moons were predictable events, visible from Earth, and potentially useful as cosmic timekeepers. Among these moons was Io, which orbits Jupiter with remarkable regularity, disappearing into Jupiter's shadow and reappearing again on a precise schedule, or so it seemed. The Danish astronomer Ole Rømer, working in Paris alongside Giovanni Domenico Cassini, noticed something odd. The predicted eclipses of Io did not always occur exactly when calculations said they should. Sometimes they arrived late, sometimes they arrived early, and the discrepancy followed a pattern. When Earth was moving away from Jupiter in its orbit, Io's eclipses appeared increasingly delayed. When Earth was moving toward Jupiter, the eclipses occurred earlier than expected. The Moon itself had not changed its orbit. Jupiter had not changed its pace. The only thing that had changed was the distance the light had to travel. Rømer proposed a bold explanation. Light, he suggested, took time to cross space. When Earth was farther from Jupiter, the light from Io's eclipse had farther to go, and so it arrived later. When Earth was closer, the light had a shorter journey and the event was seen sooner. This was not a precise measurement in the modern sense. Rømer could not calculate an exact value for the speed of light with high accuracy. His estimate was rough and, by today's standards, quite far off. But that was beside the point. What mattered was the conclusion. Light had a finite speed. This was the first time in history that the speed of light was not merely suspected, but demonstrated through observation. Not in a laboratory, but across the scale of the solar system. The universe itself had become the measuring device. The conceptual shift was enormous. Light was no longer an instantaneous messenger. It was something that travelled, accumulated delay, and could be timed given enough distance. Space was not just an empty stage, it had extent that even light needed time to cross. Other astronomers refined the idea. Later measurements using stellar aberration, conducted by James Bradley in the 18th century, confirmed that light speed was finite and measurable through entirely different means. Again, the value was not exact, but the conclusion was consistent. By the 19th century, advances in optics and instrumentation finally allowed terrestrial measurements to catch up. Experiments by Hippolyte Fizeau and later Léon Foucault used rotating mirrors and toothed wheels to measure light over known distances on Earth. These experiments produced increasingly accurate values, all converging on the same immense number. Light was fast, staggeringly fast, but it was not infinite. By this point, the question of whether light had a speed was settled. The question of what that speed was could be refined indefinitely with better tools. But a deeper issue had quietly emerged alongside these successes. The measurements all assumed something that no one had yet seriously challenged. They assumed that the speed of light behaved like other speeds, that it would depend on motion, that it would vary depending on how fast the source or observer happened to be moving. After all, every other speed known to physics behaved that way. A stone thrown from a moving cart carried the cart's motion with it. Sound waves travelled faster or slower depending on wind. Even water waves change speed relative to the flow beneath them. Motion always layered on motion. Light so far had only been measured in situations where this assumption was not truly tested. Romer's observations showed that light took time to travel. Fizeau and Foucault showed that time could be measured. But none of these experiments addressed the deeper question of how light speed behaved when measured from different states of motion. That question would turn out to be far stranger than anyone expected. At this stage, however, restraint is useful. The achievement here is already substantial. Humanity had managed to measure something that once seemed immeasurable, using ingenuity rather than brute force, patience rather than speed. Light had been caught in transit, timed, compared, quantified. The universe had yielded a number. What no one yet realized was that this number would refuse to behave like an ordinary number at all. By the early years of the 20th century, physics had reached an uncomfortable pause. Experiments were becoming more precise, instruments more sensitive, and measurements more reliable. Yet the results refused to line up neatly with the assumptions that had guided science for centuries. Light, in particular, had become a persistent troublemaker. The problem was no longer a lack of data. The speed of light had been measured repeatedly, using different methods, by different researchers in different countries. The outcome was consistent. Light in empty space always travelled at the same speed. It did not matter how fast the source was moving. It did not matter how fast the observer was moving. Motion, which normally shaped every other speed in physics, appeared to have no influence at all. Classical mechanics had no comfortable place for such behaviour. Into this unsettled landscape stepped Albert Einstein, a young patent clerk working in Bern, Switzerland. In 1905, a year that would later be called his miracle year, Einstein published a series of papers that reshaped physics. One of them addressed the growing tension surrounding light and motion. Einstein did not begin by proposing a new experiment. He did not attempt to repair the ether or adjust existing equations. Instead, he made a radical decision. He took the experimental results at face value. Rather than asking how light might behave differently to fit classical expectations, he asked what would have to change if light's behavior was already correct. At the heart of Einstein's approach were two simple statements, known as postulates. They were not derived from deeper theory. They were chosen because they matched what experiments consistently showed. The first postulate stated that the laws of physics are the same in all inertial frames of reference. In plain terms, this means that no experiment performed at constant speed can reveal whether a laboratory is moving or standing still. There is no preferred state of rest. Motion at constant velocity is relative, and the laws of nature do not care who is moving and who is not. This idea was not entirely new. It echoed principles already present in classical mechanics. But Einstein's second postulate was far more unsettling. The second postulate stated that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer measuring it. Not approximately the same, not usually the same, exactly the same. Einstein did not attempt to explain why this was true. He did not suggest a hidden mechanism or an underlying substance enforcing it. He simply accepted it as a fact of nature, supported by overwhelming experimental evidence. That choice was the turning point. By treating the constancy of the speed of light as a foundational rule rather than a problem to be fixed, Einstein shifted the burden of explanation elsewhere. If light's speed could not change, then something else had to. That something turned out to be space and time themselves. Before this moment, space and time were treated as separate and absolute. Space was a fixed stage where events occurred. Time flowed uniformly, ticking forward at the same rate for everyone, everywhere. Clocks could be synchronized once and trusted forever. Lengths could be measured once and agreed upon universally. Einstein's postulates quietly dismantled those assumptions. If the speed of light is the same for all observers, then measurements of distance and duration cannot be. Something must give. Otherwise, observers in motion relative to one another would inevitably measure different speeds for the same beam of light, which experiments clearly showed they did not. The conclusion was unavoidable. Time must adjust. Space must adjust. Measurements that seemed obvious and absolute were, in fact, dependent on motion. This was not philosophical speculation. It followed directly from insisting that the speed of light remained fixed. Einstein showed that observers moving relative to one another would disagree about how long events lasted and how far apart objects were, yet still agree on the speed of light. Clocks would tick at different rates. Lengths would contract along the direction of motion. Events that seemed simultaneous to one observer would not necessarily be simultaneous to another. None of this required exotic forces or mechanical distortions. It emerged naturally from the two postulates alone. What made this approach especially striking was its economy. Einstein did not add complexity to physics. He removed it. The ether, once thought essential, became unnecessary. There was no longer a need for a universal medium of rest. Light did not require a background to propagate through. It simply moved, and the universe adjusted around it. The idea was initially unsettling even to Einstein himself. He later remarked that it took years to fully absorb the consequences of what he had written. Other physicists were cautious. Some resisted. Others were intrigued but uncertain. Yet the mathematical consistency was undeniable, and experimental support soon followed. Measurements of fast-moving particles, precise timing experiments, and later technologies such as particle accelerators and satellite navigation all confirmed the predictions of special relativity. Time dilation and length contraction were not abstract curiosities. They were measurable effects, verified again and again. It is important to note what Einstein did not do. He did not explain why light has the speed it does. He did not derive that number from deeper principles. he did not claim to know its ultimate origin. The speed of light entered the theory as a given, a constant woven into the structure of reality rather than explained by it. This restraint was deliberate. Einstein understood that forcing an explanation where none was supported by evidence would weaken the theory rather than strengthen it. Accepting the constant allowed physics to move forward cleanly, without inventing unseen mechanisms to preserve outdated assumptions. In this way, special relativity was less an answer than a reorganization. It did not resolve every mystery surrounding light. Instead, it provided a framework in which those mysteries could exist without contradiction. The consequences were profound. Space and time were no longer independent. They became aspects of a single structure, linked by the speed of light. Motion was no longer something that happened within space and time. It shaped them. From this point onward, the speed of light was no longer just a measured quantity. It became a central feature of how reality is organized. It set the scale at which familiar intuitions break down and new ones take their place. This chapter establishes that shift. Once the constancy of light speed is accepted as fundamental, everything else must be reconsidered in relation to it. Concepts that once felt solid become flexible. Measurements that once felt universal become local. The rule is simple, the consequences are not, and with that rule in place, the quiet but far-reaching effects of a universe built around a single, unchanging speed begin to unfold. Once light had been measured and timed, it seemed natural to assume it would obey the same rules as every other moving thing. Classical mechanics had worked extraordinarily well for centuries. It described falling objects, flying projectiles, orbiting planets, and rolling carts with impressive accuracy. One of its simplest expectations was that speeds add together. If a person walks forward on a moving ship, their speed relative to the shore is the speed of the ship plus the speed of their steps. If a sound is carried by the wind, it arrives sooner when the air is moving in its favor and later when it moves against it. Motion layers neatly on top of motion. Nothing about this behavior feels controversial or subtle. So when light was shown to have a finite speed, most physicists assumed it would follow the same pattern. Light emitted from a moving source should carry that motion with it. Light measured by a moving observer should appear faster or slower, depending on the observer's direction of travel. The rules seemed clear. What remained was to test them. By the 19th century, technology had finally reached a point where this question could be addressed directly. Precision optics, stable clocks, and careful experimental design allowed scientists to look for small differences in light speed under controlled conditions. The task was no longer to measure light speed itself, but to see whether that speed changed when motion entered the picture. To make sense of how light might move, physicists relied on an analogy that had served them well elsewhere. Waves, as far as anyone knew, always traveled through something. Sound waves move through air. Water waves move through water. Vibrations pass through solids. It seemed reasonable that light, understood as a wave, must also travel through a medium. That hypothetical medium became known as the luminiferous ether. The ether was imagined as an invisible substance filling all of space, including the empty regions between planets and stars. Light waves would ripple through it, just as sound ripples through air. If this were true, then motion through the ether should affect how fast light appeared to travel, depending on direction and speed. The Earth, moving in its orbit around the Sun at roughly 30 kilometers per second, should be ploughing through this medium. As it did so, light travelling along the direction of Earth's motion should behave differently from light travelling across it. The difference would be tiny, but measurable, with sufficiently sensitive equipment. This idea was not speculative guesswork. It was a clear, testable prediction grounded in the physics of the time. Enter Albert Michelson and Edward Morley. Michelson, already renowned for his work on precision measurement, collaborated with Morley to design an experiment capable of detecting Earth's motion through the ether. The device they built, known today as an interferometer, split a beam of light into two paths at right angles, sent them on equal journeys, and then recombined them. If the Earth were moving through the ether, one beam should encounter a slight headwind while the other moved across it. That difference should change the time it took for the beams to complete their paths, producing a detectable shift in the interference pattern when they recombined. The experiment was exquisitely sensitive. Michelson estimated it could detect changes in light speed far smaller than anything previously measurable. The apparatus was mounted on a massive stone slab, floated on a pool of mercury, allowing it to rotate smoothly and sample different directions of motion. The expectation was not dramatic. No one anticipated a revolutionary result. The goal was simply to measure the effect and move on. But the effect never appeared. No matter how the apparatus was oriented, no matter the time of day, no matter the season of the year, the interference pattern remained stubbornly unchanged. Light travelled at the same speed along both paths, as though the Earth were not moving at all. This was deeply unsettling. The experiment was repeated. The apparatus was refined. Sources of error were hunted down and eliminated. Michelson and Morley were cautious scientists not prone to bold claims. Yet the result remained the same. There was no detectable ether wind. Light speed did not change with the motion of the Earth. The outcome became known as a null result. But there was nothing empty about its implications. The experiment had not failed. It had answered the question it set out to ask. The answer was simply not the one anyone expected. Physicists attempted to rescue the ether idea by modifying it. Perhaps the Earth dragged the ether along with it. Perhaps objects moving through the ether physically contracted in the direction of motion, masking the effect. Such proposals grew increasingly elaborate, adding layers of adjustment to preserve the underlying assumption. But each fix felt less satisfying than the last. The core problem remained untouched. According to the best measurements available, light speed appeared completely indifferent to ordinary motion. It did not care how fast the source moved. It did not care how fast the observer moved. It behaved as though motion itself no longer mattered. This was not a small discrepancy. It struck at the heart of classical mechanics. If speeds did not add for light, then one of the most basic assumptions about motion was incomplete. And yet the evidence was relentless. By the late 19th century, the situation had become uncomfortable rather than chaotic. The mathematics of physics still worked beautifully in most domains. Experiments continued to confirm established laws, but light stood apart, quietly refusing to fit. What made the situation especially striking was the quality of the measurements. This was not a matter of crude instruments or ambiguous data. The experiments were among the most precise of their time. The absence of the expected effect was itself the result. Light was behaving as though there were a preferred speed built into nature, one that could not be altered by motion through space. That realization did not immediately overturn physics. Instead, it lingered, unresolved, waiting for an explanation that did not rely on invisible substances or increasingly strained assumptions. The numbers were clear, the apparatus was sound, the logic of the experiment was solid. Motion had stopped mattering, at least where light was concerned. Something deeper was at work. Once the speed of light was accepted as unchanging, Something familiar had to give way. That something was time. At first, this feels like an overreaction. Time does not appear flexible. Seconds tick forward. Clocks advance. Days pass. Nothing in ordinary experience suggests that time itself might behave differently, depending on motion. Yet if light always travels at the same speed for every observer, then time cannot flow identically for all of them. This is not a philosophical claim. It is a practical consequence. Imagine two observers moving relative to one another, each carrying a clock. If both measure the same beam of light and both obtain the same speed, then their measurements of distance and duration cannot match. If distance refuses to change, then time must. If time refuses to change, then distance must. Einstein's framework allows both to adjust, but time is the first to reveal the effect. This adjustment is known as time dilation. Time dilation does not mean that time slows down in some vague or metaphorical sense. It means that when two observers move relative to one another, they will measure different amounts of elapsed time between the same events. Each observer's clock functions normally from their own perspective. The difference appears only when comparisons are made. The reason traces back to light. One way to picture this involves a simple clock built from light itself. Imagine a pulse of light bouncing between two mirrors, ticking once each time it completes a round trip. For an observer at rest with the clock, the light travels straight up and down. The distance is fixed. The ticking is regular. Now consider the same clock observed from the side as it moves past at high speed. From that viewpoint, the light follows a longer angled path as the mirrors move sideways while the pulse travels. Because the speed of light must remain constant, the light cannot move faster to compensate. It must take longer to complete each tick. The clock still works. It still ticks steadily. But it ticks more slowly relative to the observer watching it move. This is not a flaw in the clock. It is not a trick of perception. It is a direct consequence of insisting that light speed never changes. Time quite literally adjusts itself. This effect is tiny at everyday speeds. At walking pace, the difference is unimaginably small. Even at the speed of a commercial aircraft, the change amounts to fractions of a billionth of a second. But small does not mean unreal. The effect has been measured. One of the most famous confirmations came in the early 1970s, when physicists Joseph Herfel and Richard Keating carried atomic clocks aboard commercial airplanes. Some were flown eastward, some westward, while identical clocks remained on the ground. When the airborne clocks were compared with those that stayed behind, they no longer agreed. The differences were exactly what Einstein's theory predicted, once both speed and gravity were accounted for. Time aboard the aircraft had elapsed at a slightly different rate. Atomic clocks made this possible. Unlike mechanical clocks, which are influenced by temperature, vibration and wear, atomic clocks rely on the natural oscillations of atoms. These oscillations are extraordinarily stable. Modern atomic clocks can lose or gain less than 1 second over millions of years. When such clocks disagree, the disagreement cannot be dismissed. Time dilation is not confined to aircraft. It plays a practical role in technologies used every day. Satellite navigation systems rely on precise timing to determine position. Signals sent from satellites orbiting the Earth must be time-stamped accurately, or navigation errors accumulate rapidly. Satellites move quickly relative to the Earth's surface, and they also experience weaker gravity. Both effects influence how time passes for the onboard clocks. If these differences were ignored, navigation systems would drift by kilometers each day. They are not ignored. Corrections based on relativity are built into the system from the start. Engineers do not debate whether time dilation exists. They account for it as a routine part of design. Institutions such as the National Institute of Standards and Technology regularly test and refine atomic clocks, confirming that time dilation behaves exactly as predicted across different conditions and velocities. The effect is not exotic. It is measurable, predictable, and consistent. What makes this especially striking is that time dilation does not depend on how fast something feels like it is moving. There is no sudden threshold, no dramatic transition. The effect increases smoothly with speed, remaining small until speeds approach that of light itself. As velocity increases, the discrepancy grows. At speeds near that of light, the difference becomes dramatic. From one observer's perspective, another's clock can appear to slow almost to a halt. Yet from the moving observer's own frame, their clock behaves normally. It is the comparison that reveals the difference. This symmetry is crucial. Time dilation is not about one clock being wrong and another being right. Each clock faithfully records the passage of time along its own path through space-time. The disagreement arises because those paths are different. This brings the focus back to light. If light's speed were allowed to change, time would not need to adjust. Observers could simply measure different speeds and move on. But the experimental evidence does not allow that option. Light speed remains fixed, leaving time with no choice but to accommodate. That accommodation reshapes intuition. Time is no longer a universal backdrop ticking away identically for everyone. It becomes personal, tied to motion and position. Two observers can separate, reunite, and find that different amounts of time have passed for each of them, without any contradiction or paradox. This idea often sounds more dramatic than it needs to be. Time dilation does not mean that time is fragile or illusory. It means that time is physical. It responds to conditions in the same way distance and motion do. Einstein himself emphasized this point. He did not describe time dilation as time misbehaving. He described it as time behaving consistently under a new set of rules. Those rules are not arbitrary. They follow directly from the requirement that light speed remain the same for all observers. Once that requirement is accepted, time cannot remain rigid. This chapter establishes that time is not an independent quantity floating above the physical world. It is woven into the fabric of motion and measurement. It stretches and compresses as needed to preserve the constancy of light. That realization changes how duration is understood, but it also prepares the ground for an equally unsettling companion idea. If time adjusts to preserve light speed, then distance must be capable of doing the same. And when space begins to behave in this flexible way, the familiar geometry of the world is no longer quite what it once seemed. Once time is allowed to adjust itself, space cannot remain untouched. The two are not separate compartments of reality, each minding its own business. They are linked responses to the same underlying rule. If light speed must remain fixed, then distance must become flexible in exactly the same way duration does. This flexibility reveals itself as length contraction. Length contraction is often introduced as a strange visual effect, as though objects somehow squeeze themselves while moving. That description is misleading. Nothing feels compressed from within the object itself. A ruler carried along at high speed does not feel shorter to the person holding it. Their measurements remain perfectly ordinary. The change appears only when that ruler is measured by someone moving relative to it. When an object travels at high speed, close to the speed of light, observers who see it moving will measure its length along the direction of motion as shorter than when it is at rest. not slightly shorter by coincidence, but by an amount that depends precisely on its speed. This is not a mechanical deformation. The object is not being squashed by motion or stressed by acceleration. The contraction arises from how space and time divide themselves up when light speed is held constant. To see why, it helps to think carefully about how length is measured in the first place. Measuring the length of a moving object requires knowing where its front and back are at the same moment. That phrase sounds simple, but it hides an assumption. The phrase, "at the same moment," already depends on how time is defined and synchronized. In everyday life, this assumption causes no trouble. Clocks can be synchronized easily. Signals travel fast enough that differences are negligible. Space feels fixed. Time feels shared. But once time is allowed to behave differently for different observers, that simplicity disappears. Two observers moving relative to one another do not agree on which events occur simultaneously. What one observer considers now may not line up with another observer's now. This difference is not a mistake or a failure of coordination. It is a built-in feature of how time adjusts to preserve light speed. Because length measurements rely on simultaneity, disagreements about time inevitably lead to disagreements about distance. For an observer watching an object move past at high speed, the events marking the front and back of the object at the same moment are not the same events that define the object's length in its own rest frame. The result is a shorter measured length along the direction of motion. The faster the object moves, the greater the effect becomes. At low speeds, the contraction is too small to notice. At speeds approaching that of light, it becomes dramatic. An object can appear half its rest length, a quarter, or even less, depending on how close its speed comes to light's fixed pace. Yet, just as with time dilation, this effect is symmetric and consistent. Each observer measures the other's moving lengths as contracted. There is no preferred frame, no hidden state of rest. Space adjusts itself differently for each observer in motion. This adjustment is not arbitrary. It follows directly from the same constraint that governed time. Light speed remains fixed, so distances measured along the direction of motion must change to compensate. It is tempting to think of time dilation as the cause and length contraction as the consequence. In reality, neither comes first. They emerge together as a pair. Time stretches, space shrinks. Both are responses to the same requirement. This point was understood even before Einstein formalized it. The Dutch physicist Hendrik Lorentz developed mathematical descriptions showing how lengths and times would have to transform to preserve light's speed. At the time, these transformations were interpreted as physical distortions caused by motion through the ether. Einstein's insight was to remove the ether entirely and recognize that these transformations were not mechanical effects acting on objects, but structural features of space and time themselves. Once that shift is made, length contraction stops being mysterious. Space does not shrink because objects move. Space adjusts because light speed does not. This distinction matters. It reframes length contraction as a necessary feature of consistency rather than a bizarre side effect of motion. The effect has been confirmed experimentally, though not always in the intuitive way imagined. Directly measuring the length of a rapidly moving object is challenging. Instead, confirmation comes from particle physics, where unstable particles created in accelerators travel at speeds close to that of light. From the particle's own perspective, its lifetime is normal. From the laboratory's perspective, time dilation allows it to survive longer than expected. At the same time, the distance it travels before decaying is consistent only if length contraction is taken into account from the particle's frame. Both effects appear together, reinforcing one another. Institutions such as CERN routinely observe these effects in high-energy experiments. Particles that should decay almost immediately manage to traverse detectors many meters long. The observations match predictions only when both time dilation and length contraction are included. Again, these are not abstract ideas. They are required to make sense of real data. What often causes confusion is the directionality of the effect. Length contraction occurs only along the direction of motion. Objects do not shrink sideways or vertically. A moving spaceship does not become thinner or flatter. Only its length along its path of travel is affected. This specificity is not an accident. It reflects the role of light signals used to define simultaneity along the direction of motion. Space adjusts where timing disagreements arise. Where timing agrees, space remains unchanged. Seen this way, length contraction is less about objects changing shape and more about how space assigns coordinates under motion. The deeper lesson is that space and time are no longer independent concepts. They are coordinated adjustments made to satisfy a single constraint. Neither can remain rigid without forcing light speed to vary, which experiments refuse to allow. Once this coordination is recognized, it becomes misleading to talk about time dilation without length contraction, or vice versa. They are two sides of the same transformation. Together, they ensure that all observers, regardless of motion, measure the same speed for light. This coordination also dissolves many apparent paradoxes. Scenarios that seem contradictory when space and time are treated separately become consistent when both are allowed to adjust together. The mathematics remains clean. The logic remains intact. What changes is intuition. Space, once imagined as a fixed grid stretching endlessly and uniformly, becomes responsive. It stretches and shrinks depending on motion. Distances that feel solid and unchanging in everyday life turn out to be context-dependent. This does not make space unreliable, it makes it precise. Space behaves exactly as it must to preserve the deeper consistency of physical law. It does not distort arbitrarily. It responds in a measured, predictable way, tied directly to velocity and light's fixed speed. By this point, the pattern should be clear. Light does not adapt itself to motion. Motion adapts itself to light. Time slows, space contracts, measurements reorganize, all to ensure that one rule remains intact. With both time and space now revealed as flexible, it becomes natural to stop treating them as separate ingredients altogether. They are no longer independent backgrounds against which events unfold. They are intertwined aspects of a single structure. Understanding that structure requires a shift in perspective, one that treats space and time not as distinct entities, but as parts of a unified framework shaped by the behavior of light itself. That framework is where the story moves next. Once both time and space are allowed to adjust, treating them as separate ideas becomes increasingly awkward. Describing one without the other starts to feel incomplete, like explaining motion while ignoring distance, or rhythm without duration. What had been revealed so far was not two independent effects, but a single coordinated response playing out in different ways. That realization was articulated most clearly by Hermann Minkowski, a former teacher of Einstein, who gave the emerging picture a new and powerful language. In 1908, Minkowski proposed that space and time should no longer be treated as separate stages on which physics unfolds. Instead, they form a single geometric structure. He called it space-time. This was not a poetic suggestion. It was a practical one. Minkowski recognized that Einstein's results made far more sense when space and time were combined into a unified framework, rather than adjusted independently. Once joined, the strange behaviors of clocks and rulers became natural consequences of geometry, rather than isolated oddities. In this view, events are no longer described only by where they happen or when they happen, but by both together. Every event occupies a position in space-time, defined by 3 directions of space and 1 of time. Motion becomes a path through this combined structure, rather than a change occurring within separate dimensions. What gives space-time its distinctive shape is the speed of light. Because light speed is fixed, it provides a natural scale for relating space and time. Distances and durations are no longer independent quantities that can be chosen freely. They are linked by how far light can travel in a given amount of time. This relationship defines what are known as space-time intervals. A space-time interval describes the separation between 2 events, taking into account both the distance between them and the time that passes from one to the other. Crucially, while observers in different states of motion may disagree about the individual distances and durations involved, they will agree on the interval itself. This invariance replaces older notions of absolute space and absolute time. Instead of asking whether 2 events are separated by a certain distance or duration alone, space-time asks whether they are separated in a way that allows influence to pass between them. Light sits at the boundary of that possibility. To visualize this, physicists often describe something called a light cone, though the idea can be understood without diagrams. Imagine an event happening at a particular moment and place. From that event, light spreads outward in all directions at its fixed speed. All future events that could possibly be affected by that original event lie within the region light can reach as it travels forward through time. All past events that could have influenced the original event lie within the region light could have travelled from in the past. These regions define the causal structure of space-time. Events outside this structure are not just distant, they are causally disconnected. No signal, no influence, no information can travel between them without exceeding the speed of light, which nature does not permit. This is where the speed of light reveals its deeper role. It is not merely the speed at which brightness travels or colours propagate. It is the speed at which cause and effect operate. It marks the boundary between what can influence what. 2 events separated by enough distance and too little time cannot be causally connected. No matter how clever the technology, no matter how powerful the signal, one cannot affect the other without violating the structure of space-time itself. This insight reshapes how motion and influence are understood. In classical thinking, cause and effect were assumed to follow a universal time order. An event happened, then another followed. Space-time shows that this ordering is not absolute. Different observers may disagree about which of 2 distant events occurred first. What they cannot disagree about is whether one could have caused the other. That distinction matters. Space-time preserves causality even while allowing time ordering to vary. Light speed provides the rule that keeps cause and effect consistent, even when observers move relative to one another. This also explains why the speed of light appears so stubbornly fixed. If it were not, causality itself would become ambiguous. Effects could precede causes in some frames of reference. The logical structure of physics would unravel. Seen this way, the constancy of light speed is not an arbitrary feature of electromagnetism. It is a structural necessity for a coherent universe. Minkowski's contribution was to make this structure explicit. By treating space-time as a unified geometry, he showed that the strange effects of relativity were not separate rules layered on top of physics, but consequences of a single underlying design. In this geometric picture, objects move through space-time along paths determined by their motion and the forces acting on them. Light follows special paths that define the boundaries of possible influence. Massive objects must remain within those boundaries. They cannot catch up to light or outrun it. Time dilation and length contraction emerge naturally from this geometry. They are not imposed corrections. They are what straight lines look like when drawn through space-time at different orientations. This idea can feel abstract, but its consequences are tangible. Particle accelerators rely on space-time geometry to predict how fast particles can be pushed and how long they will survive. Satellite systems depend on space-time calculations to synchronize clocks. Astrophysical observations interpret distant events through space-time intervals that account for both distance and time delay. Space-time is not a mathematical curiosity. It is the stage on which every physical process takes place. One of the subtler consequences of this framework is that now becomes a local concept. Each observer carries their own present moment along their path through space-time. There is no single global present shared by the entire universe. This does not mean reality is fragmented or subjective. It means reality is structured in a way that respects the limits set by light speed. Events can only influence other events within their future light cone. Information can only propagate along allowed paths. The universe remains orderly precisely because these limits exist. This understanding also dissolves many apparent paradoxes. Questions about faster-than-light communication, time travel through signals, or instantaneous influence lose their mystery once the space-time structure is respected. The answers are not matters of technology, but of geometry. The speed of light defines that geometry. By this point, light has taken on a role far larger than illumination. It has become the organizer of space-time itself. It sets the scale for distances and durations, the limits of influence, and the structure of cause and effect. What began as an odd experimental result has revealed itself as a foundational rule. Space-time is not an empty container waiting to be filled with events. It is an active structure that shapes how events relate to one another. Light traces its boundaries. Motion navigates within it. Time and space adjust to preserve its consistency. With this framework in place, the universe becomes less mysterious, not more. The strange effects of relativity are no longer surprises. They are the natural behavior of a world organized around a single, unchanging speed. And once causality itself is understood as a feature of space-time geometry, a new set of questions comes into focus. Not about how fast light travels, but about how information, influence, and connection are constrained by that speed. Those limits, and what they imply about what can and cannot happen, emerge directly from the space-time stage now fully in view. By the time space-time is understood as a unified structure, the speed of light takes on a role that goes far beyond illumination or measurement. It becomes clear that this speed is not just about how quickly light travels, but about how the universe itself maintains order. At its deepest level, the speed of light functions as the maximum speed at which cause and effect can operate. This reframing changes the question entirely. Instead of asking why light is fast, the more meaningful question becomes why anything can influence anything else at all. Whenever information is transmitted, something physical must change. A signal is sent, a particle interacts, a field is disturbed. No matter how abstract the message seems, it must be carried by some physical process. And every such process, without exception, is limited by the same speed. That limit is the speed of light in a vacuum. This means that the speed of light is not merely a property of electromagnetic waves, it is the speed of information. It is the speed at which one event can have consequences for another. Once this is recognized, the constancy of that speed begins to look less mysterious and more necessary. If information could travel faster than light, then the structure of space-time would no longer protect causality. Effects could arrive before their causes, depending on the observer's motion. The careful ordering of events that physics relies on would become ambiguous. This is not a philosophical concern. It is a logical one. In a universe governed by relativity, different observers do not agree on the timing of distant events. Two flashes of light that appear simultaneous to one observer may not appear simultaneous to another moving relative to them. This disagreement is not a flaw in measurement. It is a consequence of how time and space are linked. This phenomenon is known as the relativity of simultaneity. It reveals that "at the same time" is not a universal statement. It depends on how the observer is moving. For events that occur at the same place, all observers agree on their order. But for events separated by distance, simultaneity becomes relative. This alone is strange enough, but it becomes far more consequential when combined with faster-than-light signaling. If a signal could travel faster than light, then there would exist frames of reference in which that signal arrives before it is sent. An observer moving at a suitable speed could see the effect occur first and the cause afterward. With enough coordination, this would allow signals to be sent into the past. Not metaphorically, literally. The details of such scenarios can be subtle, but the conclusion is robust. Faster-than-light communication would destroy the consistent ordering of cause and effect. Physics would no longer be able to distinguish between what influences what. Predictions would lose meaning. This is why the speed of light is not merely a technical constraint, it is a safeguard. It ensures that, although observers may disagree about timing and distance, they will never disagree about causality. They will always agree on whether one event can influence another. The structure of space-time enforces this agreement automatically, as long as the speed of light remains the upper limit. In this sense, the speed of light acts as a boundary between the possible and the impossible. Within that boundary, causes lead to effects. Outside it, no influence can pass. This boundary is not arbitrary. It is woven into the geometry of space-time itself. Light traces out the edges of what can be connected. Everything else must remain inside those edges. Once this is understood, the idea of a universal speed limit stops feeling restrictive. It becomes enabling. Without it, the universe would be logically unstable. This also clarifies why the speed of light applies to all forms of information, not just light. Gravitational influences, for example, also propagate at the same speed. Changes in a gravitational field do not appear instantaneously across space. They travel outward, respecting the same causal structure. This was confirmed directly when gravitational waves were detected arriving from distant cosmic events, their timing matching that of light from the same sources. Different phenomena, same limit. Institutions such as LIGO Scientific Collaboration and Virgo Collaboration have provided compelling evidence that gravity obeys this same rule. Once again, the speed of light reveals itself as a universal organizer rather than a special case. The relativity of simultaneity plays a crucial role here. It ensures that no observer can exploit differences in timing to violate causality. Although observers disagree about when distant events occur, the structure of space-time prevents those disagreements from being used to send information backward in time. This balance is delicate, but it is remarkably robust. Even scenarios that seem paradoxical at first glance, such as particles appearing to influence one another across large distances, resolve themselves when the full space-time picture is considered. The speed of light remains the governing constraint, quietly maintaining order. It is worth noting that none of this requires intent or enforcement. There is no mechanism actively preventing faster-than-light signals. There is simply no room for them within the geometry of spacetime as it exists. This is why attempts to imagine ways around the speed limit often fail. They run not into technological barriers, but into logical ones. Any proposal that allows information to outrun light must also explain how causality survives. So far, none have succeeded. This chapter's role is not to shut down speculation, but to ground the speed of light in necessity rather than accident. The universe is not slow because it is inefficient. It is constrained because consistency demands it. Once the speed of light is understood as the speed of cause and effect, its constancy becomes almost inevitable. If it varied from one observer to another, the boundary between cause and effect would blur. If it could be exceeded, that boundary would collapse. Instead, it remains fixed. This does not make the universe rigid. It makes it coherent. Within this framework, immense complexity is still possible. Stars form, life evolves, signals cross galaxies. All of it unfolds within a structure that preserves order without micromanagement. The speed of light does not dictate what happens. It dictates what can happen. And by doing so, it provides the stable foundation on which every physical explanation rests. With causality now anchored to a universal limit, attention can turn toward the deeper mechanisms that operate within that limit. The fields and forces that carry information, transmit influence, and shape the interactions of matter all work within this same constraint. Understanding how they do so requires looking more closely at what light itself is and how fields propagate through space-time without ever crossing the boundary that keeps cause and effect intact. By the time the speed of light has been recognized as a limit on causation, it becomes natural to ask a quieter but deeper question: what exactly is light? For much of history, light was treated as a phenomenon rather than a thing. It illuminated objects, cast shadows, warmed surfaces, and revealed colour, but its underlying nature remained elusive. Some thinkers imagined it as a stream of particles. Others thought of it as a wave. For a long time, neither picture felt complete. The turning point came in the 19th century, well before Einstein, with the work of James Clerk Maxwell. Maxwell was not trying to explain light itself. His goal was to understand electricity and magnetism, which had been studied separately for decades. Electric charges produced forces, magnets produced forces. Currents created magnetic effects. Changing magnetic fields seemed to induce electric ones. The behavior was rich, interconnected, and confusing. Maxwell gathered these observations into a unified theoretical framework. What emerged was a set of relationships describing how electric and magnetic fields behave, how they influence one another, and how changes in one inevitably produce changes in the other. When these relationships were examined together, something remarkable appeared. They predicted waves. Not waves on water, not vibrations in air, but self-sustaining ripples in electric and magnetic fields themselves. A changing electric field would create a magnetic field. That changing magnetic field would in turn create an electric field. The process would repeat, allowing the disturbance to propagate through empty space without the need for any material medium. Even more striking was the speed at which these waves were predicted to travel. That speed was not chosen arbitrarily. It fell directly out of the theory. When Maxwell combined the known properties of electricity and magnetism, the mathematics implied a specific propagation speed determined by two fundamental constants. When the value was calculated, it matched the measured speed of light. Maxwell recognized the implication immediately. Light is an electromagnetic wave. This was a profound unification. Light, electricity, and magnetism were not separate phenomena. They were different expressions of the same underlying field. What matters here is not the mathematics, but the structure of the result. The speed of electromagnetic waves was not something added to the theory after the fact. It was built into the relationships themselves. The theory did not allow electromagnetic waves to travel faster or slower. Their speed was fixed by the properties of the fields. In other words, the speed of light appeared to be woven into electromagnetism itself. This insight arrived decades before relativity, and it quietly set the stage for everything that followed. Maxwell's theory worked extraordinarily well. It explained known phenomena and predicted new ones. Yet it carried an uncomfortable implication. If electromagnetic waves always travel at the same speed, then relative motion should not affect that speed. This clashed directly with classical ideas about motion. At the time, this problem was not fully appreciated. Many physicists assumed that electromagnetic waves, like all waves, must propagate through some medium. That medium, the luminiferous ether, would provide a reference frame in which Maxwell's equations made sense. As later experiments showed, that assumption failed. What is important here is that Maxwell's theory did not predict a speed relative to any observer. It predicted a speed relative to the structure of the fields themselves. The equations made no reference to motion through space. They described how fields evolve in time and space together. This is where classical field theory and relativity quietly meet. Einstein did not invent the speed of light as a constant. He inherited it from Maxwell. What Einstein recognized was that Maxwell's equations already contained a speed that could not be adjusted by changing reference frames. Rather than forcing electromagnetism to fit classical mechanics, Einstein allowed mechanics to adapt to electromagnetism. This connection is often overlooked. Relativity is sometimes presented as a radical break from 19th century physics. In reality, it is also a completion. It takes Maxwell's field theory seriously and extends its implications consistently. Once light is understood as an electromagnetic wave, its behavior becomes less mysterious and more structural. It does not travel at a particular speed because of friction, resistance, or effort. It travels at that speed because that is how electric and magnetic fields propagate. Nothing is pushing light along, nothing is slowing it down. The wave simply unfolds according to the rules of the field. This also explains why light does not need a medium. Electromagnetic fields are not disturbances in something else. They are physical entities in their own right. Empty space is not truly empty. It can support fields, and those fields can carry energy and momentum. Light is a pattern moving through that field structure. From this perspective, the speed of light is not a property of light alone. It is a property of the electromagnetic field, and by extension, of space-time itself. It reflects how quickly changes in the field can propagate. This insight bridges the gap between classical and modern physics. Maxwell's field theory is classical, not relativistic. Yet it contains within it a speed that behaves exactly as relativity demands. The pieces fit together more cleanly than they first appear. There is also a gentle lesson here about explanation. Maxwell's theory explains how light propagates, not why the underlying constants have the values they do. The speed of light emerges from those constants, but the constants themselves remain unexplained within the theory. This mirrors what was seen with Einstein. The constancy of light speed is accepted as a foundational feature, not derived from deeper principles. Both theories meet at the same boundary. That boundary is not ignorance, it is structure. Light's speed is not imposed by conventional measurement. It arises naturally from how fields behave. Once that behavior is fixed, the speed follows inevitably. This raises an important question. If the speed of light is built into electromagnetism, does that mean it applies only to light? Or does it reflect something more general about how all physical influences propagate? At first glance, it might seem that light is special. After all, it is electromagnetic radiation. Other forces appear very different. Gravity shapes orbits. Nuclear forces bind particles. Why should they care about a speed set by electricity and magnetism? Yet experiments suggest otherwise. As seen earlier, gravitational influences propagate at the same speed. Changes in gravitational fields do not arrive instantaneously. They travel outward, respecting the same limit. This hints that the speed associated with electromagnetism may be a feature of spacetime itself, not just one particular interaction. Maxwell's theory provided the first clear glimpse of this idea, even if its full implications were not immediately recognized. In this chapter, the goal has not been to reduce light to equations or technical detail, but to place it within a broader context. Light is an electromagnetic wave, governed by fields that carry their own structure and constraints. Its speed emerges naturally from that structure. Relativity does not contradict this picture, it deepens it. By treating the speed predicted by electromagnetism as fundamental, relativity reveals that the same speed governs causation, geometry, and the limits of influence. What began as a description of electric and magnetic interactions turns out to describe the framework of reality itself. Light, in this sense, is both ordinary and profound. Ordinary because it follows precise, well-tested rules. Profound because those rules reach far beyond illumination. Understanding what light actually is brings the discussion to a natural threshold. If its speed is embedded in one field theory and respected by others, then perhaps it is not light that sets the limit, but something deeper that light merely reveals. That question opens the door to examining whether the speed of light is unique to electromagnetism, or whether it is the universal speed at which all fundamental influences must travel. Once light is understood as an electromagnetic wave with a built-in speed, it is tempting to treat that speed as a peculiarity of electromagnetism alone. After all, light is made of electric and magnetic fields. Other forces look very different. Gravity bends orbits. Nuclear forces bind particles. Why should they all respect a speed that emerged from one particular field theory? For a time, this question lingered quietly in the background of physics. Maxwell's equations explained light beautifully, and Einstein showed how their implied speed reshaped space and time. Yet nothing in those developments, on their own, demanded that every influence obey the same limit. What gradually became clear is that the speed of light is not really about light at all. It is about masslessness. In modern physics, particles and fields fall into broad categories based on whether they possess mass. Objects with mass can be at rest. They can be pushed, slowed, accelerated, and redirected. Objects without mass behave differently. They cannot be brought to rest. They cannot move slowly. They always travel at a fixed speed through empty space. That speed is the speed of light. Photons, the particles associated with light, have no mass. This is why light never slows down in a vacuum and never speeds up beyond its familiar value. There is no rest frame for a photon. Asking what it means for light to be stationary is like asking what it means for time to stop ticking. The question itself breaks down. This behavior is not unique to light. In field theory, forces are described by fields that fill space and evolve in time. Some of these fields are associated with particles that have mass, others are not. When a field is massless, disturbances in that field propagate at a fixed speed that cannot be altered by motion or energy input. Electromagnetism is one example, but it is not the only one. Gravity, described by Einstein's later theory of general relativity, also involves a massless field. Changes in the gravitational field do not appear instantaneously across space. They propagate outward as ripples, often called gravitational waves, carrying energy and information with them. For decades, these waves were predicted but not observed. Their effects were expected to be extraordinarily small, requiring detectors capable of measuring changes far smaller than an atomic nucleus across kilometers of distance. That level of sensitivity was finally achieved in the early 21st century by facilities such as the LIGO scientific collaboration. When gravitational waves were detected directly, something remarkable was confirmed. The waves arrived at exactly the speed predicted by relativity, the same speed associated with light. In one particularly striking observation, light and gravitational waves from the same distant cosmic event were detected nearly simultaneously, despite having travelled for more than 100 million years. The tiny difference in arrival time was fully consistent with known physical processes at the source, not with any difference in propagation speed. Gravity, like light, respects the same limit. This immediately rules out the idea that the speed of light is merely an electromagnetic curiosity. It points to something deeper, a shared constraint that applies to all massless fields, regardless of their physical nature. In this context, the phrase speed of light becomes slightly misleading. It survives for historical reasons, but its meaning has broadened. What it really denotes is the maximum speed at which any influence can propagate through space-time. A more accurate description would be the speed of space-time itself. This may sound abstract, but it captures an essential truth. Space-time is not an inert backdrop. It has structure. That structure determines how disturbances travel, how information spreads, and how cause and effect are ordered. Massless fields move at the characteristic speed of that structure. Massive objects cannot reach it, no matter how much energy is supplied, because doing so would require infinite energy. Massless excitations, by contrast, are always locked to it. This is why the same speed appears in so many places. It governs electromagnetic waves. It governs gravitational waves. It governs the ultimate speed of information. It governs the geometry of space-time intervals and the boundaries of causality. From this perspective, light is not special because it sets the speed limit. Light is special because it reveals it. Electromagnetism happened to be the first field in which this limit was clearly visible, thanks to Maxwell's equations. Gravity confirmed it later, through observation rather than theory alone. Other interactions, though more complicated, fit into the same pattern when examined carefully. This also clarifies why no experiment has ever succeeded in exceeding the speed of light. The limit is not imposed by friction, resistance, or technical difficulty. It is not something that might be overcome with better engines or cleverer designs. It is a structural feature of reality. Trying to exceed it is like trying to draw a triangle with 4 corners. The problem is not that it is difficult. It is that the concept itself is incompatible with the rules of the system. There is a subtle but important shift here. The speed of light is often spoken of as the fastest speed anything can travel. That is true, but incomplete. A more precise statement is that it is the speed at which space-time allows massless influences to propagate. Everything else must remain below it. This also helps explain why the speed appears the same to all observers. It is not a speed measured through space-time, like a car driving along a road. It is a feature of space-time itself. Changing observers does not change space-time structure. It only changes how paths through that structure are described. Once this idea is absorbed, many apparent puzzles soften. Why does light not slow down when emitted from a fast-moving source? Because it is not carrying the source's motion with it. It is moving along space-time's own geometry. Why does gravity propagate at the same speed? Because gravitational disturbances are features of space-time geometry as well. Why does information refuse to travel faster? Because doing so would require stepping outside the causal structure space-time enforces. Seen this way, the speed limit is not an add-on, it is foundational. This prepares the ground for a deeper shift in thinking. If the speed of light reflects space-time structure, then understanding that speed fully requires understanding space-time at its most fundamental level. Up to this point, the discussion has relied largely on classical ideas. Fields, waves, geometry, and smooth space-time have provided a coherent picture. But nature does not stop there. At very small scales, space-time itself may not behave smoothly. Fields may not be continuous. Particles may blur into probabilities. The classical picture, while powerful, may be incomplete. The next step is to ask how this universal speed limit fits into the quantum description of reality, whether massless particles behave differently when quantum effects dominate, and whether the constancy of this speed survives intact when the fabric of space-time itself is examined at its smallest scales. That question marks the transition from classical certainty to quantum subtlety, where light's role becomes even more intriguing than before. By the time light is examined through the lens of relativity, it already appears unusual. It ignores ordinary rules of motion, fixes the structure of space-time, and defines the limits of causation. When quantum mechanics enters the picture, light becomes stranger still, but also clearer in an unexpected way. In the quantum world, light is not described as a continuous wave spread smoothly through space. It appears instead as discrete packets of energy, known as photons. These are not tiny glowing beads flying through space, but quantized excitations of the electromagnetic field. Each photon carries a specific amount of energy, determined by the frequency of the light. This idea was introduced in the early 20th century by Max Planck, and later developed by Albert Einstein, who showed that treating light as quantized was essential for explaining phenomena such as the photoelectric effect. Light sometimes behaved like a wave, but in key situations it behaved unmistakably like a particle. The result was not a contradiction, but a dual description. Light exhibits what is known as wave-particle duality. In some experiments, it spreads out, interferes with itself, and produces patterns characteristic of waves. In others, it arrives in individual localized events, transferring energy in discrete amounts. Both descriptions are accurate, but neither is complete on its own. This duality can sound unsettling, but it is better understood as a limitation of classical categories. Light does not switch between being a wave and being a particle. It is a quantum object that does not fit neatly into either concept. The behavior observed depends on how it is measured and what aspect of it is being probed. What remains consistent across all descriptions is its speed. Photons always move at the speed of light in a vacuum. They do not slow down. They do not speed up. They do not pause. There is no experimental situation in which a photon is observed traveling more slowly through empty space. The reason lies in a subtle but important idea. Photons have no rest frame. For an object with mass, it is always possible, at least in principle, to move alongside it. One can imagine matching its speed, stepping into its frame of reference and describing it as stationary while the world moves around it. This is true for cars, spacecraft, electrons, and even atoms. For photons, this is impossible. There is no frame of reference in which a photon is at rest. Attempting to move alongside a photon would require travelling at the speed of light, which massive objects cannot do. The very notion of a photon being stationary has no physical meaning within the theory. Because there is no rest frame, there is no way for a photon to move more slowly. Speed, in this case, is not something that can vary. It is fixed by the structure of space-time and by the photon's lack of mass. This explains why quantum mechanics does not allow photons to slow down in a vacuum. There is no state in which that could occur. When light passes through materials such as glass or water, it does appear to slow. But this is not because photons themselves are moving more slowly between atoms. Instead, the interaction between light and matter causes delays as energy is absorbed and re-emitted. Between interactions, individual photons still travel at the same fundamental speed. In empty space, with nothing to interact with, there is no mechanism for delay. Quantum theory reinforces this picture rather than undermining it. Photons are described by wave functions that evolve according to precise rules. These rules do not permit solutions corresponding to slower-than-light propagation in a vacuum. The allowed states are tightly constrained. This also clarifies why light behaves differently from massive quantum particles. Electrons, for example, also exhibit wave-particle duality. They can interfere with themselves and behave in ways that defy classical intuition. But electrons have mass. They possess a rest frame. Their speeds can vary. They can be accelerated gradually from rest to near light speed, but never reach it. Photons occupy a different category altogether. In quantum field theory, which unifies quantum mechanics with special relativity, photons arise as excitations of a massless field. This masslessness is not an incidental property. It is what locks their behavior to the universal speed limit. Once again, the speed of light appears not as a feature imposed on light, but as a consequence of deeper structure. Wave-particle duality sometimes invites misleading questions. People ask whether light is really a wave or really a particle. Quantum mechanics suggests that this is the wrong question. Light is neither in the classical sense. It is a quantum entity whose behavior cannot be fully captured by either picture alone. What matters for the present discussion is that both pictures agree on one point. Whether treated as a wave or as a stream of photons, light propagates at the same fixed speed in a vacuum. There is no quantum loophole that allows light to sneak around this rule. Even phenomena that seem exotic at first glance, such as quantum tunneling or entanglement, do not violate this constraint. Tunneling does not involve signals traveling faster than light. Entanglement produces correlations without transmitting usable information. In every case, the causal structure enforced by the speed of light remains intact. This consistency is one of the quiet strengths of modern physics. Quantum mechanics and relativity are often portrayed as uneasy partners, but when it comes to light speed, they are in complete agreement. Photons behave exactly as they must to preserve causality. Another way to see this is through energy. For massive particles, increasing speed requires increasing energy. As speed approaches that of light, the required energy grows without bound. For photons, the situation is reversed. Their energy is tied to their frequency, not their speed. Changing a photon's energy changes its color, not how fast it moves. This separation is crucial. It ensures that energy can be transferred, absorbed, and emitted without ever altering the speed of propagation. Light can be red or blue, weak or intense, sparse or abundant, but it cannot be slow. Quantum mechanics also reinforces the idea that light speed is deeply connected to space-time rather than to any mechanical process. Photons do not carry clocks. They do not experience time passing in any meaningful sense. The interval between emission and absorption, from the photon's perspective, is undefined. This does not mean that light experiences no time in a poetic sense. It means that the concept of proper time, which applies to massive objects, does not apply to massless ones. The mathematical framework simply does not assign a ticking clock to a photon. Once again, the absence of a rest frame explains the result. Seen from this angle, light's unwavering speed is not something quantum mechanics struggles to explain. It is something quantum mechanics naturally accommodates. The theory leaves no room for alternatives. This brings the discussion back to limits. Quantum theory allows strange behaviors, superpositions, and probabilities that defy classical expectation. But it does not relax the speed limit. If anything, it makes that limit more secure by embedding it into the allowed states of fundamental fields. Light in the quantum world remains a messenger that cannot dawdle. This chapter's role is to show that the speed of light survives the transition from classical physics to quantum physics unchanged. The language shifts, the concepts deepen, but the constraint remains exactly where it was. That persistence is telling. If a rule holds across classical mechanics, relativity, electromagnetism, gravity, and quantum theory, it is unlikely to be accidental. It suggests a boundary that future theories will need to respect, not discard. The next question is how far that boundary extends. Whether it is merely a feature of known particles and fields, or whether it reflects an even deeper limit built into the foundations of physical law. Exploring that question requires stepping closer to the edges of theory, where energy, mass, and space-time itself begin to impose absolute constraints that no known process can cross. Those constraints define not just how light behaves, but what the universe ultimately allows. As light reveals its quantum nature and its unyielding speed, another question naturally takes shape. If light always moves at this pace because it has no mass, why can massive objects never reach it, no matter how much energy is applied? At first glance, this seems like a problem of engineering rather than physics. Faster engines, better fuels, stronger materials. With enough ingenuity, why not keep accelerating until the gap finally closes? The answer lies not in practicality, but in structure. In everyday experience, adding energy increases speed in a fairly straightforward way. Push a bicycle harder and it goes faster. Press the accelerator in a car and the car responds. Even aircraft and rockets behave according to this familiar pattern. More energy means more speed. This intuition holds well at low velocities, but it begins to fail as speeds approach that of light. According to relativity, as an object with mass accelerates, its resistance to further acceleration increases. This resistance is sometimes described as increasing inertia. The object becomes progressively harder to push. Not because of friction or drag, but because of how energy, motion, and space-time interact. The closer the object's speed comes to that of light, the more pronounced this effect becomes. At modest speeds, the increase is negligible. At higher speeds, it becomes significant. Near light speed, it becomes overwhelming. This behavior is not arbitrary. It follows directly from how energy and momentum are related in a relativistic universe. In classical physics, momentum increases linearly with speed. Double the speed, double the momentum. Energy behaves similarly. These relationships feel simple and intuitive because they work well in everyday conditions. Relativity replaces these relationships with ones that account for the fixed speed of light. As speed increases, energy contributes less to increasing velocity and more to increasing inertia. The object's motion through space-time tilts further toward the time dimension and less toward the spatial ones. The result is that each additional unit of energy produces a smaller increase in speed than the one before it. This process has no final step. No matter how much energy is added, a massive object can only approach the speed of light, never reach it. The speed acts like an asymptote. The closer the object gets, the steeper the climb becomes. Reaching the speed of light would require an infinite amount of energy. This is not a figure of speech. It is a precise statement about the structure of the equations that govern motion. There is no clever workaround, no shortcut, no alternative path hidden in the mathematics. Infinite energy is not difficult to obtain. It is impossible. This is why the speed of light is not a technological limit. It is not something that might be overcome with future advancements. It is a boundary built into how energy and motion relate to space-time itself. Even the most powerful particle accelerators ever constructed cannot change this. Facilities such as CERN routinely accelerate particles to speeds astonishingly close to that of light. Protons in the Large Hadron Collider reach more than 99.9999% of light speed. Yet they never cross it. As more energy is added, the particles do not significantly increase their speed. Instead, their energy increases their effective inertia. They become harder to deflect, harder to accelerate further, but no faster in any meaningful sense. This behavior has been measured with extraordinary precision. It is not inferred indirectly. It is observed directly in how particles respond to magnetic fields, how tightly they curve, and how much energy is required to alter their paths. The lesson is consistent. Mass and light speed are incompatible. This incompatibility explains why photons behave so differently. Photons have no mass, so they do not experience this runaway increase in inertia. There is no gradual ramp-up. They are born moving at light speed and remain there. There is no lower speed for them to occupy. Massive objects, by contrast, are anchored to slower speeds by their very existence. It is tempting to imagine that mass is merely an added property, something that could be shed or neutralized with the right trick. Physics offers no such option. Mass is not an accessory. It is a fundamental feature that determines how an object moves through space-time. This brings the discussion back to geometry. In the space-time picture, objects trace paths determined by their speed and energy. Light follows special paths that sit at the boundary between time-like and space-like motion. Massive objects must remain inside that boundary. They cannot touch it, let alone cross it. As speed increases, the object's path through space-time rotates closer to the light-like direction. But it can never align fully. That final alignment is reserved for massless entities alone. This geometric interpretation makes the energy requirement intuitive. To rotate a path all the way to the light boundary would require infinite effort. The structure of space-time simply does not allow it. Once again, the speed of light reveals itself not as a barrier placed in the way of progress, but as a defining feature of the landscape. This also explains why there is no observable transition at the boundary. Objects do not suddenly behave strangely as they approach light speed. The changes are smooth, continuous and predictable. The difficulty increases gradually without ever producing a sharp cutoff. The universe does not snap. It resists gently but inexorably. Occasionally, popular descriptions suggest that mass increases with speed, as though objects literally gain mass as they accelerate. This language is sometimes used for intuition, but it can be misleading. What actually increases is resistance to acceleration, not rest mass itself. The distinction matters because it emphasizes that the limit arises from motion and energy, not from objects physically becoming heavier in some absolute sense. Modern physics prefers to say that energy and momentum increase while mass remains constant. The effect is the same. Acceleration becomes progressively harder as speed increases, and the speed of light remains unattainable. This perspective also clarifies why no amount of clever timing or staged acceleration can bypass the limit. Accelerating in steps does not help. Each step encounters the same structural resistance. The universe is not being stubborn. It is being consistent. This consistency is one of the reasons relativity integrates so smoothly with other areas of physics. The same energy constraints that govern particle motion also shape nuclear reactions, astrophysical processes, and cosmological evolution. Stars shine because mass can be converted into energy, but even that conversion respects the same limits. Energy release does not propel matter to light speed. It emerges instead as radiation, carried away by massless particles that already live at the boundary. The boundary remains intact. This chapter's purpose is not to discourage imagination, but to anchor it. Understanding why massive objects cannot catch up to light is essential for understanding what energy actually does in the universe. Energy is not a universal accelerator. It is a way of reshaping how objects move through space-time within fixed constraints. Those constraints are not arbitrary. They follow from the same structure that governs light, causality, and geometry. Once this is appreciated, the speed of light stops looking like a goal to be chased. It becomes a reference point, a dividing line that separates different kinds of motion. On one side lie massless entities that move inevitably at that speed. On the other lie massive objects, forever approaching but never arriving. Bridging that divide requires infinite energy, which means it cannot be bridged at all. This understanding naturally leads to a deeper question. If energy, mass, and motion are so tightly interwoven, then what exactly is their relationship? How does mass encode energy, and how does space-time geometry govern both? Answering that requires turning attention to one of the most famous and most misunderstood relationships in physics, where mass and energy are revealed as two expressions of the same underlying quantity. That relationship completes the picture of why light speed stands where it does, and why nothing with mass can ever reach it. By this point, the speed of light has revealed itself as more than a limit on motion. It shapes time, space, causality, and the behavior of both massless and massive objects. At the center of all these ideas sits a relationship so familiar that it is often taken for granted, yet so deep that its consequences are still unfolding. It is the relationship between energy and mass. This connection was articulated most clearly by Albert Einstein, not as an isolated insight, but as a natural outcome of special relativity. It showed that mass and energy are not separate substances, but two expressions of the same underlying physical quantity. In everyday thinking, mass and energy feel very different. Mass is solid. It occupies space. It resists motion. Energy feels more abstract. It flows, transforms, and dissipates. One can hold a mass in the hand. Energy is felt only through its effects. Relativity dissolves that distinction. According to Einstein's framework, mass is a concentrated form of energy. An object at rest still possesses energy by virtue of its mass alone. That energy is not kinetic. It does not come from motion. It is intrinsic. This idea is often summarized by a compact mathematical statement, but its meaning is far richer than any shorthand suggests. Written out in full, the relationship says that energy equals mass multiplied by the speed of light multiplied by the speed of light. The appearance of the speed of light here is not decorative. It is essential. The speed of light acts as a conversion factor between mass and energy. It tells us how much energy is associated with a given amount of mass. Because the speed of light is so large, even a small amount of mass corresponds to an enormous amount of energy. This is not a theoretical curiosity. It is observed directly in nature. In nuclear reactions, a tiny fraction of mass is converted into energy. The mass lost is almost imperceptible, yet the energy released can power stars, fuel reactors, or produce devastating explosions. The sun shines because mass is steadily being converted into energy in its core, radiated outward as light and heat. What matters here is not the scale of the energy, but the structure of the relationship. Mass does not contradict the speed limit, it reinforces it. Because mass itself is a form of energy, accelerating a massive object does more than increase its speed. It increases its total energy. As speed increases, more and more energy is required to achieve smaller and smaller gains in velocity. The speed of light appears again as a boundary. The relationship between mass and energy explains why this boundary cannot be crossed. To reach the speed of light, a massive object would need to convert all of its mass into kinetic energy, and then require additional energy beyond that. The demand escalates without limit. This is not because mass is stubborn or poorly behaved. It is because mass already carries energy, and that energy is tied to the structure of space-time through the speed of light. Massless particles behave differently precisely because they do not possess this intrinsic energy at rest. Photons, for example, carry energy, but none of it is associated with rest mass. All of their energy is bound up in motion itself. There is no stored reservoir that resists acceleration. As a result, they do not need to be pushed up to the speed of light. They are born there. This distinction between massive and massless entities is not arbitrary. It emerges naturally from the energy-mass relationship. Massive objects have energy even when stationary. That energy anchors them to slower speeds. Massless objects do not. Their energy is inseparable from their motion, locking them to the universal speed limit. The speed of light thus appears in two roles at once. It limits how fast massive objects can move, and it defines the conversion between mass and energy. These are not separate functions. They are aspects of the same structure. This helps clarify a common misunderstanding. It is sometimes suggested that converting mass into energy might allow objects to exceed the speed of light. In reality, the opposite is true. Converting mass into energy removes mass from the system, and the resulting energy is carried away by massless particles that already move at light speed. Nothing crosses the boundary. The boundary is simply respected in a different form. Even the most energetic processes in the universe follow this rule. Supernovae release vast amounts of energy, but they do not propel matter faster than light. The energy escapes as radiation and neutrinos, not as superluminal debris. Black hole mergers release energy in the form of gravitational waves, which travel at light speed, not faster. Again and again, the same pattern appears. The energy-mass relationship also reshapes how inertia is understood. Resistance to acceleration is not just a property of mass as substance. It is a manifestation of energy content. The more energy an object has, the more resistant it becomes to changes in motion. As speed increases, energy increases. As energy increases, inertia increases. The feedback loop tightens as the speed of light approaches, making the boundary impossible to reach. This feedback is smooth and continuous. There is no sudden wall, no abrupt failure. The universe does not need to intervene forcefully. The structure does the work on its own. This also explains why the speed of light remains the same for all observers. Because it appears in the energy-mass relationship, changing frames of reference does not change its role. Observers may disagree about how energy and momentum are distributed, but they agree on the boundary those quantities cannot cross. Seen this way, the speed of light is not imposed from outside physics. It emerges from the internal consistency of energy, mass, and space-time geometry. This consistency is what allows physics to scale. The same relationship governs subatomic particles and galaxies. It shapes the behavior of atoms and the evolution of stars. It constrains particle accelerators and supernova remnants alike. The energy stored in mass also explains why even empty space is not truly empty. Fields carry energy. Vacuum fluctuations carry energy. Space-time itself responds to energy and mass, bending and evolving in response. This is where the discussion begins to expand outward. If mass and energy are interchangeable, and if energy shapes space-time, then the distribution of mass and energy across the universe must influence how space-time behaves on the larger scales. Expansion, curvature, and cosmic evolution all become linked to this same relationship. The speed of light appears again, not as a local limit, but as a global organizer. It determines how quickly changes in mass and energy can influence distant regions. It sets the pace at which the universe can respond to itself. It governs how structure grows and how information spreads across cosmic distances. This chapter's role is to anchor the speed limit in one of the most fundamental relationships in physics. The link between mass and energy does not undermine the constancy of light speed. It demands it. Once mass, energy, and space-time are understood as facets of a single framework, the speed of light becomes unavoidable. Remove it, and the relationships unravel. Keep it, and everything fits together. This prepares the ground for looking outward. If the speed of light shapes how energy and mass behave locally, it must also shape how the universe behaves as a whole. The expansion of space, the propagation of signals across cosmic time, and the limits of observation all flow from the same structure. The next step is to follow this relationship beyond laboratories and particles, and into the large-scale behavior of the universe itself, where the speed of light quietly governs what can be seen, influenced, and known. When the discussion shifts from laboratories and particles to the universe as a whole, the speed of light takes on another quiet role. It becomes the messenger that carries information across cosmic distances, linking distant regions of space and time. Yet the universe itself is not static. It is expanding, and that expansion raises an important question. If space is stretching, what happens to light as it travels through it? At first glance, expansion sounds like motion. Galaxies appear to be moving away from one another. Distances increase. Space itself grows. It is tempting to imagine light being dragged along, slowed down, or somehow altered by this process. But that intuition turns out to be misleading. The key point is simple, though its implications are subtle. Cosmic expansion does not change the local speed of light. Wherever light is measured in any small region of space, it still travels at the same fixed speed. That rule remains intact. Expansion does not break it. Instead, expansion changes the space through which light moves. To understand this, it helps to separate two ideas that everyday language tends to blend together. One is motion through space. The other is the expansion of space itself. When a car drives down a road, it moves through space. Its speed can be measured relative to the road, other cars, or the surrounding landscape. This kind of motion obeys the familiar rules of relativity. Cosmic expansion is different. Galaxies are not flying through space away from one another like debris from an explosion. Rather, the space between them is increasing. The coordinates that define distance stretch over time, carrying galaxies along without requiring them to move locally at high speed. Light traveling through this expanding space continues to move locally at its usual speed. But because the space it traverses grows while the light is in transit, the journey changes character. One visible consequence of this process is redshift. As light travels across the expanding universe, its wavelength is stretched along with space itself. The crests of the wave become farther apart. The light shifts toward longer wavelengths, moving from blue toward red and beyond into infrared or radio. This stretching does not require light to slow down. It changes the scale of the wave, not the speed at which it propagates locally. Redshift is not a Doppler effect in the usual sense, though the two are often compared. A Doppler shift arises when a source moves through space. Cosmological redshift arises because space itself changes while light is moving through it. This distinction matters. In the Doppler case, speeds add and subtract in familiar ways. In cosmic expansion, there is no single frame in which all motion can be described as ordinary velocity. The expansion applies everywhere, uniformly, altering distances rather than pushing objects. Because of this, it is possible for very distant galaxies to recede from us at an effective rate greater than the speed of light, without violating relativity. This statement often causes confusion, but the resolution lies in the difference between local speed and global separation. No galaxy outruns light locally. No object moves through space faster than light. But the space between distant regions can grow so quickly that the distance increases faster than light could cross it. This does not allow information to travel faster than light. Signals sent from such distant regions may never reach us, not because they travel too slowly, but because the space they must cross keeps expanding. Once again, the speed of light remains the governing limit on causation. Observational cosmology relies heavily on this behavior. By measuring the redshift of light from distant galaxies, astronomers can infer how much the universe has expanded since that light was emitted. The greater the redshift, the more the universe has stretched during the light's journey. This method has been used for decades, refined through careful observation and increasingly powerful instruments. Space telescopes have played a central role in this work. Observatories such as the Hubble Space Telescope have mapped galaxies across vast distances, revealing a universe filled with structure and motion. More recently, the James Webb Space Telescope has extended this view, detecting light that has been stretched so far by expansion that it now lies in the infrared. These observations confirm a consistent picture. Light arriving from the distant universe behaves exactly as expected when both its fixed local speed and the expansion of space are taken into account. Crucially, none of this undermines the speed of light rule. At every point along its path, light moves at the same speed relative to its immediate surroundings. The stretching occurs gradually, distributed across space and time. There is no moment at which light suddenly violates its limit or behaves anomalously. This reinforces an important lesson. The speed of light is not a restriction on how far things can be separated. It is a rule about how influence propagates locally. Cosmic expansion respects this distinction perfectly. In fact, the expanding universe makes the role of light speed even clearer. Because information cannot outrun light, there is a horizon beyond which events cannot influence us. This cosmic horizon is not a physical boundary, but a limit set by expansion and light speed combined. Light emitted beyond a certain distance will never arrive, no matter how long one waits. The universe expands too quickly for the signal to keep up. This does not imply that the signal is too slow. It reflects the geometry of space-time on the larger scales. Here again, the speed of light shapes what can be known. Astronomers speak of the observable universe not because anything lies beyond observation in principle, but because light from beyond that region has not had time and may never have time to reach us. The boundary is set by expansion and by light's finite speed acting together. This has a calming implication. The universe does not hide its secrets arbitrarily. It reveals them according to consistent rules. What can be observed is governed by structure, not chance. It also underscores why expansion does not conflict with relativity. Relativity governs local physics. Expansion governs global geometry. The two coexist without contradiction. Even as the universe expands, light continues to trace its structure faithfully. It carries information forward in time, stretched but not distorted, slowed or accelerated. Its speed remains the same in every small patch of space it passes through. This consistency allows cosmology to function as a precise science rather than a speculative one. Measurements of redshift, brightness, and distance can be combined to reconstruct the history of cosmic expansion. The same speed of light that limits communication also enables reconstruction. It sets the scale for interpreting signals across billions of years. From the earliest light released after the universe cooled enough for atoms to form, to the glow of distant galaxies seen today, light has been the primary witness to cosmic history. That light has travelled through an evolving universe without ever changing its local behaviour. In this sense, expansion does not compete with the speed of light. It works alongside it. Light provides the ruler and the clock. Expansion provides the stretching of those rulers and clocks over time. Together, they define what can be seen and how it must be interpreted. As observations improve, the picture becomes more detailed, but the underlying rules remain the same. The universe grows, space stretches, light moves at its constant speed, wavelengths lengthen, information propagates within fixed limits. The story scales cleanly from the smallest measurements to the largest distances. This chapter's role is to show that even on cosmic scales where intuition strains, the speed of light remains untouched. Expansion changes distances, not the rules of motion. Redshift alters wavelengths, not local speeds. The universe can be vast, dynamic, and evolving without ever relaxing its most fundamental constraint. And that brings the discussion back to observation itself. If light is the messenger and its speed is fixed, then careful measurement of that light becomes the most reliable way to test the universe's laws across time and space. The next step is to look more closely at how those measurements are made, how precise they have become, and how the speed of light has been confirmed not just in theory, but through observation across scales far beyond anything achievable on Earth. By this stage, the speed of light has appeared so consistently across so many areas of physics that it begins to feel less like a measured quantity and more like a structural feature of reality. That impression is not accidental. Modern science does not merely assume the speed of light is constant. It has tested that assumption to extraordinary precision. The story of how this is done is quieter than dramatic discoveries or bold theories, but it is just as important. In the early days of measuring light, uncertainty dominated. Instruments were limited, distances were short, clocks were imperfect. Each new method improved the estimate, but always with margins of error that left room for doubt. Light was known to be fast, but how fast exactly remained a moving target. Over time, that changed. Advances in laser technology, atomic clocks, and interferometry transformed measurement from approximation into precision. Light could be produced at stable frequencies, guided along carefully controlled paths, and timed against clocks whose regularity surpassed anything previously imaginable. By the late 20th century, the situation had quietly reversed. The limiting factor was no longer uncertainty in the speed of light, but uncertainty in the instruments used to measure distance and time. This led to a subtle but profound shift. Instead of treating the speed of light as something to be measured again and again, physicists began treating it as a reference, a fixed value against which other measurements could be calibrated. Light was no longer chasing definition, it was providing one. Today, the speed of light in a vacuum is defined exactly. It is not subject to experimental refinement. It does not come with an error bar. It is a fixed number, chosen to anchor the system of units used to describe space and time. Written out in full, the definition states that light travels exactly 300 million meters in 1 second. This does not mean that scientists stopped measuring light. It means they reached a point where further measurements would tell them more about their rulers and clocks than about light itself. Distance is now defined in terms of how far light travels in a given fraction of a second. Time is defined by atomic transitions whose behavior is linked to fundamental physical constants. The speed of light sits at the center, tying these definitions together. This approach reflects confidence, but not complacency. Organizations responsible for maintaining measurement standards, such as the International Bureau of Weights and Measures, continually test the consistency of these definitions. Atomic clocks are compared across continents. Laser frequencies are stabilized and cross-checked. Satellite links allow timing signals to be exchanged with astonishing accuracy. In these tests, the speed of light never wavers. What does change occasionally is understanding of how best to realize the units built upon it. Improvements in clock technology, for example, refine how the second is implemented in practice. Laser interferometers refine how distances are realized. The definitions themselves remain fixed, serving as anchors rather than targets. This shift from measurement to definition can feel counterintuitive. It might seem like science has decided to stop questioning a value. In reality, it reflects the opposite. It reflects the recognition that the speed of light has become one of the most stable features in all of experimental physics. Defining it does not shield it from scrutiny. It acknowledges that scrutiny has already reached its practical limit. Importantly, this does not mean that certainty has replaced inquiry. Physicists remain open to the possibility that deeper theories could one day reframe how the speed of light is understood. What they do not expect is that its value will begin to drift, vary by direction, or depend on motion. Such behavior would have shown up long ago in precision experiments. Modern tests look for exactly these possibilities. Highly sensitive experiments search for tiny violations of symmetry. Astronomical observations compare light arriving from different directions and different epochs. So far, every test reinforces the same conclusion. Light speed is the same everywhere it can be measured. This reinforces certainty without claiming finality. The speed of light is treated as exact within current physical theory, not because science has closed the book, but because all available evidence supports that treatment overwhelmingly. If future discoveries demand revision, definitions can change. For now, stability is the most honest description. There is also a philosophical dimension to this choice. By defining the speed of light, science acknowledges that measurement is always relational. distances and durations do not exist independently of the methods used to measure them. Anchoring those methods to a universal constant provides coherence across disciplines and scales. It allows laboratory experiments, satellite navigation, particle physics, and cosmology to speak the same language. This coherence is not imposed arbitrarily. It emerges from decades of consistent results. The certainty surrounding the speed of light is therefore not dogmatic. It is cumulative. It is the product of countless checks, refinements, and cross-comparisons that all converge on the same outcome. At the same time, this certainty is carefully bounded. Physicists do not claim to know why the speed of light has the value it does. They do not claim it could not have been different under other conditions or in other possible universes. They simply recognize that, in this universe, it behaves as an exact constant to the limits of observation. This distinction matters. Certainty about behavior does not require certainty about origin. One can rely on a rule while still wondering why it exists. That balance between confidence and curiosity is one of the strengths of modern physics. It allows practical systems to function reliably, while leaving room for deeper questions to remain open. As measurement has become more precise, the speed of light has shifted roles. It began as an unknown to be estimated. It became a quantity to be refined. It is now a foundation upon which other measurements rest. Few physical quantities have made that journey. The result is a quiet kind of trust. Not trust born of assumption, but trust earned through repetition. Light has been asked, in countless ways, to betray variation. It has never done so. This chapter's role is to establish that trust clearly and honestly. The speed of light is not treated as fixed because it is convenient. It is treated as fixed because everything we know says it is. Yet that trust does not end the conversation. It sharpens it. Once a constant is accepted as foundational, attention naturally shifts from whether it varies to what it means, why it occupies such a central role, what its existence implies about the structure of reality itself. Those questions are not answered by more precise measurements. They require reflection, interpretation, and a careful look at what physics is really telling us about the universe. That turn from measurement to meaning marks the transition from empirical confirmation toward the deeper implications that lie beneath the numbers. By now, the speed of light has earned a remarkable status. It appears in electromagnetism, relativity, quantum theory, gravity, and cosmology. It defines causality, shapes space-time, limits motion, and anchors measurement itself. With so many roles, it is natural to ask whether this speed is truly fundamental, or whether it might be an emergent feature of deeper laws yet to be uncovered. This question sits at the boundary between established physics and careful speculation. Within all tested theories so far, the speed of light behaves as a fundamental constant. It does not vary with location, direction, energy, or time. It does not drift. It does not fluctuate. Experiments have searched for deviations across enormous ranges of scale and precision, and none have been found. Yet physics has learned to be cautious about declaring anything final. History offers many reminders that quantities once thought absolute later turned out to arise from deeper structures. Temperature, for example, feels fundamental in everyday life, but emerges from the collective motion of particles. Pressure feels basic, yet it is a statistical effect. Even solidity dissolves into fields and forces under closer inspection, so it is reasonable to ask whether the speed of light might belong to this category. One possibility explored in theoretical physics is that the speed of light reflects the properties of space-time itself, rather than standing apart from them. In this view, light speed is not an independent input, but a feature that emerges from how space-time responds to energy and motion at large scales. This idea remains speculative, but it is not careless. Some approaches to quantum gravity, which aim to reconcile quantum mechanics with general relativity, suggest that space-time may have a discrete or granular structure at extremely small scales. At those scales, the smooth geometry assumed by relativity may no longer apply exactly. If space-time behaves differently at such scales, it is natural to wonder whether constants defined within that geometry might also be affected. Importantly, there is no experimental evidence that the speed of light changes under these conditions. Any such effects, if they exist at all, would likely be suppressed far beyond current observational reach. The speculation concerns the origin of the constant, not its observed behavior. Another line of inquiry asks whether the speed of light could vary in extreme environments, such as near black holes or during the earliest moments of the universe. These ideas are explored cautiously, often as mathematical possibilities rather than physical claims. So far, every observation remains consistent with a constant speed. Even in the strongest gravitational fields known, light follows paths predicted by relativity. Its speed locally remains unchanged. What changes is the geometry through which it moves. This distinction is crucial. General relativity already allows for complex behavior without altering the local speed of light. Time slows near massive objects. Space curves. Paths bend. Yet at every point, light still moves at the same pace relative to its immediate surroundings. Any theory proposing a varying speed of light must therefore explain not only how the variation arises, but why it has escaped detection so completely. That is a high bar. Most modern physicists treat the speed of light as fundamental within our current understanding, while remaining open to the possibility that future theories may reinterpret its role rather than revise its value. This is a subtle but important distinction. Reinterpretation does not mean replacement. It means finding a deeper framework in which the constant appears naturally, perhaps as a conversion factor, a symmetry constraint, or a geometric property. This is similar to how Einstein reinterpreted gravity. He did not replace Newton's law with something contradictory. He revealed a deeper picture in which gravity emerged from space-time curvature while preserving Newton's results in appropriate limits. A future theory might do something similar with the speed of light. It might reveal why space-time has the structure it does, why massless fields propagate at a single invariant speed, why causality is protected so robustly. The constant itself might remain unchanged, even as its meaning deepens. This cautious attitude is characteristic of modern theoretical physics. Physicists distinguish carefully between what is known, what is inferred, and what is imagined. The speed of light belongs firmly in the first category when it comes to behavior. Its constancy is among the most secure results in science. Questions about its ultimate origin belong to the third category. They are interesting, motivating, and worth exploring, but they are not conclusions. It is also worth noting that many speculative ideas are constrained by the very consistency they seek to explain. Any deeper theory must reduce to known physics in ordinary conditions. It must preserve causality. It must respect the observed behavior of light across scales. This severely limits what is possible. As a result, even bold theoretical frameworks often leave the speed of light untouched, building their novelties elsewhere. They may quantize space-time, introduce new dimensions, or alter the nature of particles while keeping the speed limit intact. In that sense, the speed of light functions as a stabilizing feature. It anchors theory as much as experiment. This does not make physics conservative. It makes it disciplined, Speculation is welcomed, but it must be framed clearly as speculation. It must acknowledge the strength of existing evidence rather than dismiss it. The question is not whether the speed of light might change tomorrow, but whether its role could be explained more deeply tomorrow. That is a quieter, more productive question. From a broader perspective, the speed of light has already achieved something rare. It has unified vast domains of physics without strain. Classical fields, relativistic geometry, quantum particles, gravitational waves, and cosmic expansion all accommodate it naturally. That level of coherence is not easily discarded. So is the speed of light truly fundamental? Within everything currently known, the answer is yes. It behaves as a foundational constant, not an approximation, not an emergent average, and not a provisional placeholder. Whether it remains fundamental in a future, deeper theory is an open question. But even there, the most likely outcome is not that the constant disappears, but that its presence is explained more fully. The distinction matters because it shapes how the discussion proceeds. If the speed of light were unstable or poorly understood, the preceding chapters would rest on shaky ground. Instead, they rest on one of the firmest pillars in physics. This chapter's role is not to undermine that pillar, but to show that curiosity does not stop at certainty. Confidence in a constant does not preclude wonder about its origin. The universe has given us a rule that works everywhere we have looked. Asking why that rule exists is not a rejection of what is known. It is an invitation to understand it more deeply. With that perspective in place, the discussion can now turn toward synthesis, toward bringing together the threads of measurement, geometry, causality, fields, energy, and cosmology into a single, coherent picture. Not to resolve every question, but to see clearly what the speed of light has already revealed about the structure of reality. Imagining a universe in which the speed of light were different is a useful exercise. Not because such a universe is likely or even possible, but because it reveals how much structure quietly depends on that single constant. The aim is not to picture catastrophe or spectacle, but to notice how delicately balanced the relationships of physics really are. The first thing to understand is that changing the speed of light would not simply make things faster or slower. It would alter the relationships between space, time, energy, and causality at a fundamental level. The equations that describe motion, fields, and interactions are not built around arbitrary numbers. They are tuned to one another. Changing one element ripples through the rest. If the speed of light were higher, the most immediate effect would be subtle rather than dramatic. Time dilation and length contraction would become less pronounced at everyday speeds. Objects could move faster before relativistic effects became noticeable. For human experience, the universe might feel more classical, more Newtonian, across a wider range of conditions. But that apparent simplicity would come at a cost. The relationship between mass and energy depends directly on the speed of light. Increasing that speed would increase the amount of energy associated with a given amount of mass. Nuclear reactions would release vastly more energy. Stars would burn differently. The balance between radiation pressure and gravity that stabilizes stars would be altered, possibly making long-lived stars like the Sun impossible. If the speed of light were lower, the opposite problems would arise. Relativistic effects would intrude much earlier. Time dilation would become noticeable at speeds far below those achievable by everyday technology. Energy requirements for acceleration would grow rapidly. Chemical and nuclear processes, which depend on precise energy balances, could behave very differently. Atoms themselves might not be stable in the same way. The forces that bind electrons to nuclei depend on electromagnetic interactions, which are governed by the same constants that set the speed of light. Altering that speed would shift the scales at which these forces operate. The sizes of atoms, the strengths of bonds, and the spectrum of light emitted by matter would all change. This is where instability, rather than destruction, becomes the key theme. Physics is full of interlocking relationships. Constants do not float independently. They form ratios and combinations that determine whether structures can exist at all. Change one too much, and the others no longer align in a way that permits complexity. Causality would also be affected. If the speed of light were higher, the boundary between cause and effect would widen. Influences could propagate more quickly, allowing distant regions to remain more tightly connected. That might sound beneficial, but it would also compress the distinction between local and global behavior. Systems that rely on separation and delay to remain stable could become overly coupled. If the speed were lower, causality would tighten, horizons would shrink, regions of the universe would fall out of causal contact more easily. Coordination across space would become harder. Even modest separations could isolate systems from one another. In extreme cases, the universe could fragment into causally disconnected patches far earlier in its history. The expansion of the universe would also behave differently. The balance between expansion speed and light speed determines what can be observed and what can influence what. A different speed of light would shift cosmic horizons, altering which regions could ever exchange information. Structure formation, the growth of galaxies and clusters, depends on signals travelling outward, coordinating collapse over vast distances. Change the speed at which those signals propagate, and the large-scale structure of the universe could look entirely different. None of this requires explosions or collapse to make the point. It is enough to see that familiar patterns depend on precise relationships. Even the notion of measurement would be affected. Our definitions of distance and time are built around the speed of light. Change that constant, and the coherence of measurement systems would have to be rebuilt from scratch. Units that currently align neatly across scales would drift apart. Comparing experiments performed under different conditions would become more difficult, not easier. In a deeper sense, the geometry of space-time itself would change. The division between time-like, light-like, and space-like intervals is set by the speed of light. Alter that boundary, and the classification of events shifts. Paths that were once forbidden might become allowed, or vice versa. The shape of space-time cones would change, reshaping the logic of influence. This does not mean the universe would become chaotic. It means it would be different in ways that may not support the same kinds of complexity. The lesson here is not that the speed of light is uniquely perfect in some aesthetic sense. It is that it sits within a narrow range that permits stable structures to form and persist. Too far in either direction, and the web of relationships that support matter, energy, and causality begins to unravel. Thinking through these alternatives helps explain why the constant matters. It is not important because it is large or small, fast or slow. It is important because so many independent features of reality depend on it simultaneously. It coordinates scales, it links forces, it preserves consistency. This perspective also tempers speculation. When theories propose varying constants or alternative universes, the challenge is not merely to imagine change, but to show that such change could support anything like a coherent world. That is a demanding requirement, and it explains why most serious proposals remain cautious. In our universe, the speed of light does not drift. It does not wobble. It does not adapt to circumstances. That rigidity is not a limitation. It is what allows everything else to adapt. The speed of light is less like a dial that could be turned freely and more like a keystone. Remove or alter it significantly, and the structure it supports no longer holds its shape. This is why hypothetical scenarios are useful even when they are unrealistic. They illuminate dependence. They show which features of reality are negotiable and which are not. The conclusion that emerges is calm rather than dramatic. The universe does not rely on constant vigilance to avoid disaster. It relies on stable relationships that quietly enforce consistency across scales. The speed of light is one of those relationships. By imagining what would break if it changed, it becomes easier to see what it currently holds together. Time, space, energy, causality, and structure all lean on the same support. That realization does not end the discussion, it gathers it. Having explored how the speed of light shapes motion, fields, particles, and the cosmos, and having seen how fragile that structure would be if the constant were different, the final step is to bring these threads together, not to solve a mystery, but to see clearly what has already been revealed. Across every scale explored so far, the same quiet number keeps reappearing. It shows up in the behavior of light, in the structure of space-time, in the limits of causation, in the flow of energy, and in the shape of the universe itself. By now it should feel clear that the speed of light is not merely a fast thing moving through space. It is a rule that space, time, and matter obey together. Seen this way, the story has never really been about light. From the earliest attempts to measure its speed, light acted as a messenger rather than a protagonist. It carried information, revealed delays, exposed inconsistencies, and forced revisions. Each time it was questioned, it answered in the same way, not with variation but with refusal. It would not go faster, it would not go slower, it would not adjust itself to motion. That refusal shaped everything else. When classical mechanics expected speeds to add, light declined. When ether theories tried to give it a medium to lean on, light ignored them. When measurement improved, the answer did not change. The universe adapted around the constant rather than the constant adapting to the universe. This is the first unifying thread. The speed of light acts as a fixed point. Other quantities bend and stretch around it. Time dilates, length contracts, energy rises, inertia grows, geometry reshapes. The constant itself remains still. That stillness is not passive, it is organizing. Once accepted, the constancy of light speed transforms from an experimental curiosity into a structural principle. It becomes the rule that holds together otherwise incompatible ideas. Motion remains relative. Causality remains consistent. Measurement remains coherent. Space-time emerges as a unified structure precisely because this rule must be preserved. Space and time do not flex arbitrarily. They adjust in concert. Each compensates for the other, so that the speed of light remains unchanged for every observer. This coordination is not enforced by mechanism or correction. It follows automatically from geometry. In this geometry, light traces boundaries rather than paths. It outlines what can influence what. It separates the reachable from the unreachable. It defines horizons, not walls. That definition extends far beyond optics. In the quantum world, the same constant governs which states are allowed and which are forbidden. Photons, as massless particles, have no choice but to move at this speed. Massive particles carrying rest energy are forever prevented from catching up. The boundary is clean, smooth, and absolute. Energy reinforces the rule rather than challenging it. As objects accelerate, energy does not grant freedom. It adds resistance. The closer a massive object comes to light speed, the more energy is diverted into inertia rather than velocity. The constant stands firm, not because it is guarded, but because the structure does not permit crossing. On cosmic scales, the same principle quietly persists. Space expands, distances grow, galaxies separate. Yet light continues to move locally at its fixed pace, even as the space it crosses stretches beneath it. Wavelengths lengthen, horizons form, observation becomes finite. The rule remains intact. This constancy allows the universe to be readable. Because light behaves predictably, redshift becomes a record rather than a distortion. Because causality is preserved, cosmic history can be reconstructed. Because information propagates at a fixed speed, observation becomes a reliable guide rather than a misleading echo. Measurement itself ultimately yields to the constant. Once precision improves far enough, the speed of light stops being something to chase and becomes something to anchor. Distance and time are defined around it, standards align to it, systems rely on it. The constant moves from result to reference. Yet this confidence is not rigidity. Physics remains honest about what it knows and what it does not. The speed of light is treated as exact in behavior, but its ultimate origin remains open to inquiry. That openness is not weakness, it is restraint. Speculation is allowed, but carefully framed. No serious theory treats the constant casually. Any deeper framework must explain why this speed exists, not how to avoid it. And when hypothetical universes are imagined with different values for this constant, the result is not spectacle but fragility. Structures fail quietly, relationships misalign, stability erodes. The lesson is not that the universe is finely tuned for drama, but that consistency requires balance. The speed of light turns out to be less about motion than about patience. It enforces delay, it prevents instant influence, it allows separation to matter. It ensures that causes unfold into effects rather than collapsing into simultaneity. In doing so, it gives the universe time to behave. Stars form slowly, signals travel gradually, structures emerge over billions of years. Nothing happens everywhere at once. This patience is not accidental. It is a consequence of the same constant that limits speed. There is also a kind of regularity here that is easy to overlook. The speed of light does not fluctuate with circumstance. It does not respond to environment or scale. It does not care about energy levels, directions, or observers. That indifference is what makes lawfulness possible. Because the rule does not adapt, everything else must. Because the constant is fixed, patterns can persist. Because limits exist, complexity can develop without collapsing into contradiction. This is the deeper synthesis. The speed of light is not a feature added to the universe, it is a condition the universe is built around. Geometry, causality, energy, and observation all emerge within its bounds. None of them override it. None of them escape it. Light simply reveals what was already there. By following this constant from laboratory measurements to quantum fields, from space-time geometry to cosmic expansion, the same picture repeats. Not a universe straining against a limit, but one shaped by it. The rule is quiet. It does not announce itself. It shows up only when questioned, and when it does, it answers the same way every time. No faster, no slower. That consistency is what allows physics to connect such different domains without tearing. It is why equations written for particles apply to stars, why clocks in airplanes agree with clocks in orbit, why observations made billions of years apart can be compared meaningfully. Everything leans on the same support. In that sense, the speed of light is not dramatic. It is dependable. It does not rush. It does not yield. It simply holds. Understanding this shifts perspective. Instead of seeing the universe as a collection of objects moving through space, it becomes easier to see it as a network of relations unfolding within a stable structure. Motion becomes secondary. Structure becomes primary. Light speed is the expression of that structure. And once that is seen clearly, the story naturally slows. There is no final revelation waiting beyond this point, no sudden twist. What remains is reflection rather than resolution. The constant does not explain everything. It does not answer every question. But it quietly shapes every answer that physics gives. Recognizing that is not the end of curiosity. It is the beginning of a calmer one. From here, the conversation can turn away from limits and toward meaning, away from speed and toward scale, away from explanation and toward perspective, not to conclude the story but to let it settle. The speed of light often enters conversations as a limit, a line that cannot be crossed, but seen in full context, it is less a restriction and more a defining feature of how reality holds together. It sets a rhythm rather than a barrier. Because this speed is fixed, the universe gains structure. Time unfolds instead of collapsing into immediacy. Distance matters. Causes have room to become effects. Events remain ordered, not because they must be enforced, but because the geometry of reality allows no alternative. Nothing needs to hurry. Across scales that range from subatomic interactions to the largest visible structures in the cosmos, the same quiet rule applies. Light moves steadily. Information propagates patiently. Change spreads at a pace that allows complexity to form without tearing itself apart. This reliability is what makes the universe readable. Measurements remain meaningful across generations. Observations made here can be compared with signals that began their journey billions of years ago. The same constant that governs a laboratory experiment also governs the expansion of space itself. There is comfort in that continuity. The speed of light does not promise answers. It does not explain why the universe exists or where it is ultimately going. But it provides a stable background against which those questions can be asked without confusion. It ensures that whatever unfolds does so within a framework that is consistent, predictable, and shared. Reality does not change its rules from place to place. Seen this way, the speed of light is not something to race against or overcome. It is something to orient by. It defines what can connect, what can influence, and what must remain separate. It gives the universe its scale and its patience, and within that scale everything else finds its place. From the slow formation of stars to the gentle arrival of ancient light at a telescope, the same calm boundary holds. Nothing rushes ahead of it. Nothing falls behind it. The universe moves forward together, one consistent step at a time, understanding that does not resolve every mystery. But it offers something quieter and perhaps more lasting, a sense that reality, at its deepest level, is not chaotic or hurried, but measured, lawful, and steady. A place where change happens, but never all at once. A universe shaped not by speed alone, but by the calm boundary that makes speed meaningful at all.